Welcome to the short discussion on strain energy due to the axial and shear loads. This is a part of Unit 1. The part 2, it is the strain energy. And this is no, the first unit of the Strength of Materials 1 course. So I expect or I hope that with the end of this particular discussion, the learners are able to relate to the concept of strain energy, as well as they can able to compute the strain energy due to shear and axial loads, right? So this is a no target for us. By the end of the discussion, we are supposed to learn this. Let us see how we can proceed. So let us try to first understand what is strain energy, what is the concept of strain energy. Now if you apply any external load on an elastic body, it deforms, right? Then we will say there is some work is done on the body. That where is that work going? That is actually no, we know that the energy is conservative. It will not last. So it is stored in the form of the internal energy in the body itself. That internal energy stored is what we are calling as strain energy, right? So when you remove the load, the energy will be it will be recovered, right? The no whatever the changes happen on the body, that will be regained, right? So how we can define strain energy now is it is the internal energy stored in the body or on the elastic body when you apply some external load, right? And the body gets deformed. So here the example of no clockwork can be used to illustrate the concept of strain energy. Basically, the energy builds up or stored in the wheels due to the vibration of the quartz stone that we will be using in the clocks, right? That it will store the energy by its winding action, and slowly it releases the energy by unwinding action, right? So this is about the strain energy and its application. Then in dealing with the structural members, we'll come across the strain energy in different forms, not just the axial load. It may be no strain energy may be stored because of the normal stress or direct stress, or it may be due to shear, or it may be due to bending or even torsion, right? Any of these uh, torsional, any of these loads or stresses can induce some form of strain energy in the bodies, right? In most of the no times, the strain energy concept will be using for the computation of the deflections in the structures, right? There are famous theorems like Castigliano's theorem based on the strain energy theory, right? It can be used both for the indeterminate as well as determinate structures, right? So finally, conclusion here from this particular slide that we are going to learn is the strain energy is nothing but the internal energy stored in the body, right? Or in the elastic body when we apply an external load and the body gets deformed, right? Right, this is how we can just understand the strain energy. Now let us look at the strain energy developed due to axial loads. Let us consider a uniform cross sectional rod here. It is subjected to gradually increasing load. We will be increasing the load gradually, right? So as we increase the load, the body gets deformed, so that there will be some work done in the form of the energy stored in the particular rod. So the total work done by the rod, by the load, right, for the deformation x1, right, results in the increase of the strain energy, right. So now as we are keep increasing on the load magnitude, there will be increasing amount of strain energy developed in the body. Now if you want to compute that, it is simply nothing but no uh, load times the deformation happened, right. So at a, let us say at a particular instant of time, this the deformation is 0. Later on it happens by an amount x1, right. So 0 to x1 pdx, that will give you your strain energy. Now if you consider perfectly linear elastic kind of material, or the deformations happen such as a spring, this p can be replaced with some kind of stiffness, right, kx. So p equal to kx, if you substitute, then this becomes half kx square, right, half kx square, nothing but. So when you consider the linear elastic deformation such as spring, now in that case this load becomes stiffness times the deformation, so it becomes half kx square, or kx1 square if the deformation is x1, right. So if that kx can be replaced by the load, then or force, then we'll be getting half p1 x1. This is the amount of strain energy stored in the elastic body of p1 x1. Now if you want to make the expression free from the effects of the size, then what we can do is we can divide this by the volume, right. You can say strain energy per unit volume. So strain energy per unit volume, that is called strain energy density, and that particular one is given by, right here, p by a times. So you can no but just rewrite the terms, right. So what we are doing basically for this expression, we are dividing by volume, that means area times length. So that becomes your strain energy density small u is equal to sigma x times d epsilon. Why it is like that? Because p by a we can replace by stress, and dx by L, deformation by original length, comes to the strain, right. So your expression ultimately strain energy density is nothing but the product of, or right, yeah, product of or multiplication of strain and stress, okay. So the next one is the total strain energy, whatever that was stored in the body, or total energy strain energy density that was stored in the body, is resulting from the deformation, right. So if you want to calculate that, you can find out the entire area of this, because we just now told, right, strain energy density is nothing but multiplication of stress and strain. So you can find the area of this diagram, right. There is an integration, so you can find out the area of that. In the formulation we have, right, it is a summation of the stress and summation of the product of stress and strain. So you can simply multiply the whole area, you will be getting the no total strain energy density, right. Here when the material is unloaded, not fully the no entire deformation gets no bounce back to the original position, it will not happen. Only part of that energy will be recovered, right. So as you are seeing here, this triangular portion energy will be regained. The rest of the energy is that was leaving with some permanent deformation, right. So only strain energy is represented. Now the strain energy what we are strictly calling is in terms of this particular area only. So you can just take the area of only this part. So half times sigma is the stress and strain up to here, so half times sigma times epsilon 1, right. That is what we are referring as strain energy. right? So energy resulting from, so then what about the rest of the area? The rest of the area from here to here, right? This part of the energy, right? So this one, the strain energy density in this part, right, is one and strain energy which is elastic region, whereas the other part of this, the strain energy stored is in the plastic region, right? So how long it no stays in the plastic region till the fracture happens, till the rupture happens. So the strain energy density resulting from setting from here to here, say epsilon 1 to epsilon r, the strain up to the rupture, that particular one is what we are called, that strain energy density, right? That means you take the area of the stress strain diagram in this region, that's what is called modulus of toughness, right? So the modulus already is generally defined as the ability of the material to absorb in the plastic, absorb the energy in the plastic deformation. So even in plastic deformation it absorbs the energy, right? So here basically what we discussed in but this particular slide is this part of the energy will be recovered, whereas this part of the energy will be not recovered and it is stays in the form of permanent deformation. And this particular part, when you take the area of this, right, strain energy density calculate in this region becomes your modulus of toughness. Then strain energy due to the axial loads, right? In the same no flow we are moving, ultimately we can express the strain energy due to axial loads in different forms in terms of no only strains we can do, or we can we can express in terms of stresses only, right? So when you express that term, previously you have written strain energy is nothing but product of stress and strain. So here it is E times epsilon 1 times, right, d epsilon x. So if you can integrate it, you will be getting E epsilon 1 square by 2. So this is the strain energy stored only in terms of, no, you are just using strains. Young's modulus of the material is constant. Therefore, you can, if you want to express the strain energy in terms of strains, this is the formulation. We can even write the same one only in terms of stresses, right? That is sigma 1 square by t, because we know as per Hooke's law, your epsilon 1 can be written as E, right, sigma by E. So upon simplification we will be getting this one. So strain energy we have expressed in terms of load, half times P times deformation, that is 1. Now you have seen back, right? Of times P times X. This is one form in terms of load, strain energy in, or due to axial load in terms of load, right? Strain energy stored in the body due to axial load, we can express in terms of load itself, or we can even express in terms of strains such as this, right? Then or we can express in terms of stresses such as this, right? So now what about the strain energy density? In the what strain energy density is nothing but strain energy we divide it the volume, right? That is we just now discussed the strain energy density value in this particular elastic region only. If you take, that is called modulus of resilience, right? So uy, right, that this is modulus of resilience. That means when the sigma becomes yield stress, sigma is considered, so you can take any up to any extent the sigma, right? So depending upon this entire region, sigma can be any value, but when that becomes your yield value, the sigma becomes yield stress, that particular that particular expression what you are getting, that strain energy density what we are getting, that is called modulus of resilience. So the strain energy density is represented by small u, and that is called modulus of resilience. Strain energy per unit volume of the material, right, is what we are already called strain energy density or resilience, right? When that no, stress becomes your what you call yield stress, then that becomes, right, modulus of resilience, right. Otherwise, simply resilience means strain energy per unit volume, right. Next, if that stress you consider it a proof value, no, for the materials such as no, there are some, even in steel there are some kind of steels such as high yield strength deformed bars, HYSD bars, where the yield point is not specifically identified. In those cases we will be taking proof stress as the basis. So for those cases, if you take the proof stress as a reference, that particular resilience becomes proof resilience for that material, right. So proof resilience, another name is, right, modulus of resilience. Okay. So here basically, in summary, on the concept of no, strain energy, right, is nothing but the internal energy stored in the body, right, uh, elastic body, preferably internal energy stored in the elastic body due to the application of the external load, right. So that's what we can say strain energy in summary. And the strain energy can be any one of the forms, like axial form or shear, due to shear stresses or torsional stresses. Now if you consider only the strain energy due to axial loads, so this is, we can express that in terms of load, or we can express in terms of stresses, right. If in terms of stresses is right, half sigma square by half sigma square by E, right. So in, or even in terms of strain, later on we have seen strain energy density you are expressing in multiple forms. So in any of the form you can express that. So once you have now calculated this energy in terms of load, this can be rewritten in any of these forms, right, in terms of stresses or in terms of even strain. And depending upon the uh, um, area we calculated up to either elastic limit or even plastic limit, your strain energy may be called either modulus of resilience or modulus of toughness. The next one is uh, about the strain energy developed due to axial loads. If you take a numerical, now let's look at a numerical example of the strain energy. So here